So as an example, suppose that we have a microcontrollers that typically include 10-bit ADC. 10-bit ADC. It means that using 10 bits convert analog to digital. And the voltage supply at this microcontroller is 5 volts. This is the Vmax, the maximum value for voltage that we talked in the previous section. Now, we say that if K is 500 and sampling period is 1 millisecond, calculate the corresponding quantized value at K 500 and calculate the time to generate each step in a 10-bit quantizer. It means that T delta. We learned these formulas in the previous section from here. T delta is sampling period divided by 2 to the power of B, and VQ, quantized voltage, is K times delta. And we learned that delta also can obtained using Vmax divided by 2 to the power of B minus 1. Now, according this formula, delta is equal to Vs divided by 2 to the power of B minus 1. Our bit is 10. 2 to the power of 10 will be 1024, minus 1 will be 1023. And Vs or Vmax is 5 volts. So it means that the result will be this value. Or approximately we can suppose 5 millivolts. This value is approximately equal to 5 millivolts. Now, the quantized value Vk, according to the formula, is K times delta. We calculated the delta here, and the question says K is 500. So it means that at K 500, what is this K? Actually, this K is the value of delta that occurred at this analog section. So the quantized value is 2.45 volts, and T delta is Ts divided by 2 power of B. Again, the question says Ts is 1 millisecond, and 2 to the power of B will be equal to 1024. The question will be 1 microsecond. It means that this T delta will be 1 microsecond. And the quantized value for these, for example, for the values that occurred as K500. For example, here K is 6. VQ is K times delta. At this section, VQ is K delta. K here is 11. T delta is also this section. Okay, now today I would like to talk about the digital to analog conversion. If you remember, we said that in the block diagram of each system, for example, in the block diagram of a smartphone, We will have analog to digital converter at the beginning of block diagram. For example, the outputs of sensors are analog signal. For using this analog signal to the smartphones or digital systems, we need to convert it to digital. So after some processing, at the end, we need again to convert this digital signal to analog signal. Okay, now we learned how can we convert A to D. Now we want to learn that how can we convert digital to analog. For this reason, we say that we have two methods for converting digital to analog. The first method is boxcar reconstruction, and the second method is pulse width modulation. Okay, let's talk about the boxcar reconstruction. In the boxcar reconstruction, we suppose that we can produce the rectangular pulse for the same sampling period that we convert from analog to digital. Now, the amplitude corresponds to the quantized binary value that we produced at the previous section, can be stored in the memory. So we can separate these pulses for each binary code and reconstruct the parameters according to the and reconstruct our signal according to the parameters sampling period and delta. Look at here. Suppose that this is my sampled digital signal. How can I obtain these pulse? Reversely, what did we do in the analog to digital? We suppose that this is our analog, so we sample and hold, then convert, quantize it to the binary code. Now I have the same binary code. Now, with fitting a curve for this sampled signal, I can find the blue one, which is my analog signal. Let's look at here. This is an example that we want to convert it to the analog signal. This is the sum section of a signal that is represented in oscilloscope. Oscilloscope is a device that can represent us the signal form of each waveform and also a digital or analog signal. Now, if you look at here, the large division in the horizontal axis is divided to 0.01 milliseconds, and in the vertical axis 0.5 volt. This is time, this is voltage value. If we look at here, we can find that according to figure, we can find the sample period. How can I find the sample period? If I look at the horizontal axis sample period, I understand that I have two small division for each period, two small division. Look at here, two small division, two small division. This is the period of time. Now, how can I find? I say that the large division value is 0.01 milliseconds. It means that if I want to find the value of this small division, I can divide it to the 5. 0.01 divided by 5. Now, I want to find sampling period for this signal divided by 5 times 0.01. The sampling period value will be equal to 0.04 milliseconds. This is the sample period. Sample period. And Fs, sampling rate. Sample rate is 1 divided by Ts. It means that 1 divided by 4 times 10 to the power of minus 5, which is equal to 2.5 times 10 to the power of 4 hertz. Now, the next step is finding the quantized step size. I need to find this step size. Delta. What is the value of delta? Again, I can say that each small division or section is my delta, and the large division is 0.5 volt. It means that my delta is 1 divided by 5 times 0.5 volt, which is equal to 0.1 volt. Now, suppose that my digital signal sequence is like that, and I used, for example, 6 bits. What is my sequence? I suppose that my digital signal sequence is like that: 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, and so on. First of all, I divide my digital signal into 6 bits groups and then calculate this value. What is this value? To the power of 0, 1, 2, to the power of 3. The rest of these values are equal to 0. It means that I don't need to calculate. I only need this one and this one. It means that 2 to the power of 3, 8, plus 2 to the power of 0, 0, 1. 8 plus 1 is equal to 9. What about this one? If you calculate this one, you can find that is equal to 57. Now, this is the time for finding the analog value of each section. If I multiply this value, I say VA1, for example, is 9 delta, 9 times 0.1. It means that 0.9 volts. VA2, 57 delta. It means that 5.7 volts. The second method is pulse width modulation. Now, I want to explain what is the pulse width modulation. This is so important. Pulse. Suppose that we have a square signal or pulse like that. We call the period of this signal, P, T, PWM. And the amplitude of this signal is Vmin, minimum voltage, and Vmax, maximum voltage. For example, this is the amplitude. The difference between Vmax and Vmin. Suppose that Vmin is 0, Vmax is 5. It means that the amplitude of the signal is constant and 5 volt. Now, if you look at here, at each period of time, at each TPWM, we have a section that our signal is high or on, and another section our signal is low or off. For each period, if you look at you can find that we have a period that signal is high and low, high, low, high, low. This period is called T-on. The period that signal is its high level. And T-off. The period, the duration that signal is high is called T-on. And the period and duration that signal is low is called T-off. This period is a cycle. This period is a cycle. Now, the most important concept in PWM is duty cycle. Duty cycle. We say that the duty cycle represents how much of the period in which the signal is high. So for calculating the duty cycle, we need to know how much of the period of signal is high. If my T on a high time, for example, will be 6 milliseconds, this duration. And this duration is 4 milliseconds. It means that my TPWM is 6 plus 4, 10 milliseconds. Because this is a one cycle. One cycle is one period. Now, how can I calculate duty cycle? I can say that T on divided by TPWM times 0. Now, what is T on? What is T on?
6 milliseconds.
6 milliseconds. What is TPWM?
10 milliseconds.
Times 100. It means that the duty cycle at each signal is equal to 60%. If T on be 5 milliseconds, what will be duty cycle? If T on be 5, calculate the duty cycle.
50.
50%. Now, this duty cycle is so important at this PWM signal. Why? Because, interestingly, we can find that at the output of PWM system, if we take this, for example, signal to the PWM, the voltage, output voltage of this signal is the average value of this signal. The average value. Now, how can I calculate the average value of this signal? I can say that V out is equal to duty cycle times V max duty cycle times V max. Suppose that I have this signal T PWM is equal to 8 and T on is 2. What is the V out or V average of this signal? I say that first of all I have to calculate the duty cycle. I know that duty cycle is T on divided by TBWM.
Duty cycle is the 25%.
Exactly. 1 divided by 4 and Vmax here, suppose that is 12 volts. Okay, now V out will be 1 divided by 4 times 12. It means that 3 volts. The V out of PWM will be 3 volts. I hope you learn about the concept of pulse width modulation. After learning the PWM, now we say that for converting digital to analog, we divide the T-PWM period into sub-intervals, into B bits, that we know that the bits of the digital system. Now I can say that this duration delta t is equal to TPWM divided by 2b minus 1. Now T on is equal to K delta T. K varies from 0 up to 2 to the power of b minus 1. Now, if I want to calculate the average value, that this average value is my quantized value. How can calculate the average volt value at PWM waveform? We said that T on divided by TPWM, this is duty cycle. We said that for calculating average voltage at PWM waveform, I have to multiply duty cycle to the Vmax. What was the formula of duty cycle? T on divided by PWM. With multiplying these two values together, and also I know that T on is K delta T. With substituting K delta T instead of T on, I can find that VQ, my quantized value, is equal to this value. Okay, now again, same as the boxcar reconstruction. If I know the delta value of signal, now how can I find the delta? V max divided by d to the power of b minus y. We learned it before. Now VQ is equal to K delta PWM. That varies from 0 up to V max. And here you can see that the duty cycle can be calculated like that. As an example, Suppose that we have 5-bit PWM system. The period of PWM signal is 2 milliseconds. The maximum voltage of signal is 5 volts. Now I want to calculate, for example, the value of voltage at K equal to 10. First of all, I have to calculate delta T. I say that T PWM divided by 2 power of 5 minus 1 is equal to this value, 65 microseconds. Now, the step size, we learned that can be calculated using this formula. I now Vmax TPWM delta T. So I can find that delta PWM is equal to 0.16 volt. Again, according to the quantized value, average value of PWM with multiplying K by delta, I can find the quantized value. If we suppose that my K is 10, now the quantized value will be 1.6 volt. Now, we want to find that at each K, our system will produce 2.5 volts.